Very much for having me. I'm going to run through a lot of stuff today, and I'm going to assume a lot of prior knowledge. I'm going to assume that you all, one way or another, understand how data is used for the purposes that we're all interested in, generating insights, the challenges around that, and I will also probably rehash some things that you already know, and some things which are imperfectly understood across the system, including perhaps a little more hectoring on open working methods than you might wish for. So a quick map. I'll give a brief summary of what OpenSAFELY is, just so that you're oriented. And then I'd like to discuss in quite a lot of detail, actually, the problems that we wanted to solve around disclosiveness, around pandemics calling for bigger, faster data, around open working methods. And then I'm going to describe in eye-watering detail the technical solutions that we've implemented, because I think they're really important. OpenSAFELY is all about creating tools that make it easy for people to produce high quality research in a transparent and open way, but also a very collaborative way. And I think by making open, high quality and transparent work the default and the only way that you can work is a really powerful way of delivering culture shift. Before I begin, I suppose I should say, because some people think I'm just a journalist, journalists are fine. So I trained in medicine at Oxford and then London, then trained in psychiatry at the Maudsley. I was a consultant. Well, I hit CCT anyway in 2015. I trained in epidemiology at London School of Hygiene and Tropical Medicine, and now I run a team called the Data Lab at the University of Oxford. And we're quite unusual in that we're a truly mixed team of software developers, traditional academic researchers, and clinicians, and latterly policy specialists, all pooling skills and knowledge and working collaboratively together to produce not just single academic papers, but also tools and services that turn raw data sets into useful derived objects. So you might have seen our openprescribing.net service, lets you see what every GP practice is prescribing month by month, spots outliers and so on. Lots of clever statistical process control techniques for sending people alerts, which have been written up in the BMJ because they're interesting and clever and methodologically interesting and clever, but also lots of really, really good variable design and service design, thinking about what are the insights that will best help clinicians to improve quality, safety and effectiveness. So our most recent project is OpenSAFELY, and this is a huge collaboration. So working on behalf of NHS England, who are data controller, but in broad collaboration between my group, the Data Lab, leading on software and analyses, the Electronic Health Records Research Group at London School of Hygiene for their analytics skills, and TPP and more latterly EMIS, the Electronic Health Records software companies, for their back end, but also for their outstanding and very deep knowledge on the raw data. We've now built a full open source, highly secure analytics platform running across the full pseudonymized primary care records of 55 million patients. It's just over 95% of the population. We are fully live inside TPP, covering 40% of the population, and we're fully signed off with full data access, smoke tests passed, and end stage tech development for more complex analyses inside EMIS, which covers an additional 55% of the population. And we've pursued a very new model. So for privacy, security, low cost and near real-time data access, we've built the analytics platform inside the Electronic Health Records data center of the major electronic health records software providers. So we've taken the analytics to the place where the data already resides, which brings a lot of benefits, which I'll talk about in a moment. But that's not the only privacy and security play we've made. In addition, we've also built software that uses tiered and increasingly non-disclosive tables to prevent researchers ever needing direct access to the most disclosive raw underlying data to run their analyses. But furthermore, researchers not only can researchers not download disclosive data onto their local machine, even when they come into the TRE, they cannot see it in its raw form. They don't need to see it in its raw form. Code is developed against simulated dummy data using open platforms before moving into the live data environment. And we're able to do that because we've standardized the processes of transformation of the messy raw electronic health record data into research ready data sets. And by doing that, a lot of really important things follow around the privacy engineering, but also around open working methods and allowing people to share code in a way that is informative rather than a messy dump of arbitrary SQL, R and Python scripts. So as a consequence of our improved privacy offer, we also have access to an unprecedented scale of data. We have every individual patient's full primary care GP record with all diagnoses, tests, referrals, prescriptions, and so on. And that's the full raw record, not a derivative of it. And that's all linked onto their data from various other sources, including SUS for hospital admissions, outpatients visits, and so on, ECDS and similar for coded A&E attendances, CPNS, death in hospital from COVID, which flows faster than ONS death because it comes from hospitals, but obviously only covers COVID death. SGSS, the COVID test results. ONS, very generously, thank you very much, for cause of death in and out of hospital. Household data, so we've got a household variable identifies other pseudonymized occupants, but also is it a care home, approximate location, from that obviously is derived IMD and things like that. ICNARC, the ICU data, ISERIC, detailed hospital records of hospitalised COVID patients and more. And despite this unprecedented scale of data, privacy advocates like MedConfidential have actively praised our model. So how does that happen? Well, let's just take a step back and think about some of the problems that we wanted to solve. So problem number one, in a pandemic, you need access to fast live data. Patient GP records in the UK are stored electronically as a list of event codes, as we'll discuss in more detail. And those records are commonly used for research projects by academics wanting to know whether patients from one ethnic group are more or less likely to get diabetes or something like that. And conventionally, researchers would work on intermittently extracted records for only a few million patients, which is what you see with CPRD through a conventional research data download service. And that data is commonly many months out of date when it becomes available for research. But in evaluating a new and rapidly arising cause of death or service changes, or indeed vaccine rollouts, you need data very quickly. So COVID-19, novel cause of death, never seen before, arrived suddenly, risen in prevalence very rapidly. The first wave of COVID-19 would have come, peaked and gone away entirely before any cases appeared in most conventional GP research data download services like CPRD. In addition to timely data, you also need huge numbers of patients in a research data set if you want to understand, for example, the different risks from COVID-19 in smaller subgroups of the population. Now, I realise this is likely coals to Newcastle, but I think it's really worth rehearsing. If you want to understand the different risks in people with haematological versus non-haematological cancers, for example, then very tragically, you need enough deaths or enough predicted deaths in each group to be able to assess the difference. It's the same for understanding change in risk among people on a given drug. Let's say there are 100,000 people taking a drug, which is the right answer for something like hydroxychloroquine in routine primary care treatment for things like rheumatoid arthritis. Let's say 1 in 2,000 people in the country have died from COVID-19. If your research sample only contains 10% of the population, then you'd only have an expected 5 deaths among 10,000 people taking hydroxychloroquine for your statistical models, and that will very clearly compromise the precision of your estimates. So you want fast, rapid, but also very large data sets. Another illustration of why you want very fast flowing data is our vaccine coverage reports. So posted today on medRxiv, and also I posted a Twitter stream this morning. We've got data that's between 4 and 11 days behind real time on exactly who is and isn't getting the COVID-19 vaccine, broken down by fine subgroup, not just ethnic groups, not just IMD, but also clinical subgroups, severe mental illness, learning difficulties, Down syndrome, COPD, and so on. So, challenge number 2. This kind of data is re-identifiable. Take the names and addresses off it, it is still re-identifiable. So downloads, in my view, are catastrophically dangerous. We built the OpenSAFELY platform to be as secure as possible and to protect patients' privacy, but we also wanted to allow researchers to run analyses over a very large scale of records, but also we wanted them to be able to exploit the full granularity of the detailed records. So to understand the choices we made, I think it's really useful to understand the nature of the re-identification challenge. Typically, people say, oh, we've pseudonymized the data because we've taken off the name an address or the calendar date of their birth or the last digits of their postcodes. Now, unfortunately, records that have been pseudonymized in this way are still very vulnerable to re-identification. To be clear, most researchers are, of course, trustworthy, and they're carefully evaluated to be trustworthy, and they sign documents asserting that they'll be trustworthy, and they take training encouraging them and facilitating them to be trustworthy. But to understand privacy and security risks, we talk about threat modelling, and that's completely reasonable. We work through worst case scenarios because it's important to understand and ensure that your security systems and privacy approaches are as resilient as possible within what is reasonable and practical. It's also important to reflect, I think, that people do very frequently mount re-identification attacks on these kinds of data sets. So there is a constant stream of often local newspaper stories about, you know, an ex-partner in a GP practice looks at, sorry, an administrator in a GP practice looks up their ex-partner in the records, looks up their children in the records, looks up the girls that they went to school with in the records. I also know from friends, you know, friends who are celebrities, I know from friends who are to a degree in the public eye that they have had stories about them that come about from leaks from tax databases in one case, and another database in another case that I can't talk about. So we know that people do mount re-identification attacks on these data sets, and also we know that it is possible to identify people very easily. Let me give you a concrete example. If you find one patient who had twins in 2013, another baby in 2014, and then the event codes moved from the London area to the Oxford area in 2015, that's enough to identify my wife in a GP dataset, because there's only one person who meets those characteristics in the country. Having identified the pseudonymous identifier for my wife, you could then find other aspects of my wife's medical history. You could also identify me, and you could find out all kinds of things that I don't want you to know. Now, I want people to be blocked from being able to do that kind of thing, not just to me and my wife, but to anybody. And I think it's incredibly important that we make it very clear to the public that we've done everything we can to block that kind of re-identification attack. But I also want to be able to prove to the public, by keeping good but also sensibly readable logs of all activities, that those kind of re-identification attacks have never happened, to ensure that people are not just blocked but also very rapidly detected if they try to do any of that kind of work. Next, electronic health records are really complicated. They're really hard to work with. It's really easy to mess up. It's really easy to create a code list where you think you're identifying SNOMED codes for hypertension, and then you read through somebody's code list for their paper, and it turns out that it includes pulmonary hypertension, which might be relevant in some cases, but probably not. It might include ocular hypertension, which is not the same as high blood pressure. Also, people often do their data management in a very messy way. Everybody doing different jumbles of arbitrary SQLR and Python. And you want people to be sharing in good, sensible ways, because open working really matters. I'm going to move on to some hardcore tech stuff. This is the last bit of preamble. It's 10:50. Why code sharing matters. So this is the third fundamental principle, the third fundamental challenge that we're aiming to address. We want people to share analytic code for all the work they do, not an arbitrary jumble of SQL and Python and R and bits of data management mixed up in the data analysis code in a stata_do file, but good reusable objects. And that's for a number of reasons. First up, reproducibility. Narrative descriptions of the methods used to manage and analyze data are almost always ambiguous to a greater or lesser extent. They're insufficient to help others understand or replicate the analysis. This has come up during COVID as much as before, when people are trying to understand and resolve discrepancies in the results of different analyses, for example. So PHE, OpenSAFELY, ONS and other analytic teams have produced slightly different results from adjusted models, exploring the putative additional risks associated with ethnicity on COVID-19 death. And it's unclear whether these discrepancies are partially or wholly attributable to differences in the variables that have been created, or differences in the model, different approaches to data management, variable categorization, or different data sources. And that's because the code for the OpenSAFELY ones is shared, but for the others, to a greater or lesser extent, it's unclear. Secondly, Open sharing, open working methods is important because we improve quality through open review. All research has shortcomings. Reciprocal review improves quality and helps to identify error. It'll help spot the errors in the code lists that I described earlier. And they're best caught early. Coding errors have led to really big, high-profile retractions, including a notable recent one of a retracted trial, where they got the binary variable for are you in Group A or Group B the wrong way round in their analysis, and they literally flipped the results of the trial. So you want to catch these kinds of coding errors early. And we've also, in the past, seen incorrect implementation of clinical algorithms, leading to safety concerns. Thirdly, you want code sharing because it drives efficient reuse. It takes a huge amount of work to generate analytic code, but also the data management code lists and code that process raw, messy clinical data, especially electronic health record data, but also bespoke questionnaire data in cohorts, for example, into variables that are ready for use in a statistical model. And when that work's been done once, it's useful if that work is available for review and reuse by others running a similar or identical task in the future. And that's the norm throughout, for example, the open source software community. And it's the norm in many other areas of scientific research, like physics, and also the molecule and genome people are a long way ahead of us. It facilitates also efficient innovation. Instead of repeating low value tasks, it means that you can ratchet up every time the task is done once. It's shared, it's not blindly reviewed, it's reviewed and then reused. Fourthly, and I think this is missed by a lot of people, an important aspect of the value of sharing code openly is capacity building. We certainly see in our group when analysts come in and they're approaching a new area or skill set, they can benefit from libraries of code or existing notebooks which show the tasks they're learning being practically implemented by others before them. And sharing code and libraries can also help analysts who currently use Excel and point and click manual labour in the data mines to move to more modern, robust and repeatable, efficient, reproducible script-based techniques. Lastly, and related to the issue of reuse, we want to build a modular ecosystem. Data science in health goes way beyond single analysis scripts. Lots of organisations have spent huge amounts of time and effort in creating data management and data analysis pipelines. We should be surfacing that where possible to help everybody else work. And then lastly, finally, trust and accountability. So being very diplomatic, different stakeholders have varying levels of trust in the ability of government and the NHS to make the best use of data and to protect their privacy. And sharing code openly creates an oversight mechanism. It encourages analysts to write higher quality code, and it discourages, as before, inappropriate use of data. And obviously the public, mostly, the public in quotes, because the public is us as well, it's everyone. The public mostly will not review code, but knowing that it's in public and can be audited can provide reassurance by demonstrating that there is a transparent process for review. So, 10:54, I think I can justify another 17 minutes. Here's the meat. Here are the objectives of what we set out to build with OpenSAFELY. We wanted something that had a higher security than current offers, in order to justify the higher volumes of data that we wanted to cover. We wanted no data downloads. We wanted no needless access to view the raw data, as you get in most off-the-shelf trusted research environments. But we still wanted analysts to be able to run analyses conveniently across the most disclosive raw data. We wanted all code for all data management and analysis to be shared to support open science, critical review and reuse. But we wanted it to be shared in a way that facilitated reuse in a broadly speaking, pragmatically, flexibly standardized framework. In addition to that, we needed low startup cost because we were working with very low resources. We wanted it to be completely modular. We wanted to be completely transparent to the public and others about all actions on the data, and we wanted it to be portable to other settings. So let me tell you what we've built. Number one, we built the analytics platform inside the electronic health record data center where the records already reside. Now, that sounds like a simple thing. It's actually quite an innovation, but also it brings a number of really important advantages. First up, in very basic terms, it means you're already operating inside a highly secure environment compliant with standards like ISO 27001. It means you can keep logs on every action on the data. It avoids long and difficult data transfers. So the full records of the entire population of England, or at least the key subset of records that are useful in research, amount to around 100 billion rows of data for primary care. And that's information on a sufficiently large scale that if it wasn't for COVID lockdown, you'd probably be better off putting some hard drives in your backpack and cycling to the data centre 100 miles away, rather than getting it down an NHS pipe. It also brings a lot of other less expected advantages. So OpenSAFELY is a huge collaboration across a wide range of skills, including EHR researchers, software developers and developer researchers at the Data Lab, all working on behalf of NHS England, but the EHR records, the EHR software companies themselves are a key part of the team, and they bring a huge amount of experience and knowledge because they built the systems that generate and manage this data in the first place. Now, that's not to say that we're wedded to OpenSAFELY only operating inside the EHR software vendors' data centres. It's only one part of the design principles of OpenSAFELY, and we've deliberately built OpenSAFELY to be portable code, so we can build it in the ONS SRS if you'd like us to. We're already working with NHS Digital on starting to build it in their environment. I'm a big fan of TREs. I think we need very slightly more than one TRE. We don't need 100. We need to be very cautious about explosion. And we're very happy to build OpenSAFELY as a layer in any environment. But secondly, we wanted to go beyond a conventional TRE. So there's a long history of people building things called trusted research environments, where analysts can access data without downloading it onto their local machine. But in our experience from building OpenSAFELY and from prior work, it's often hard to find any documentation on how these work without working on them directly. A typical model is that vetted researchers log into a remote desktop, Windows 7 or whatever, where they have access to a standard, familiar, interactive code development environment, a stats analysis software package. It might be Excel, but R, Stata or similar, RStudio, and the data set they've requested in the remote machine's hard drive. And there are typically controls on removing bulk data from the machine, and activities often monitored in some way. For example, recording a video capture of the screen, or keystrokes, or more sophisticated methods. And that's better than letting people download data. But depending on the implementation, some of the problems from data downloads remain. And in some respects, this approach is still like having access to the full raw data set, but just on someone else's computer. If you put a load of data on your laptop and then close it, but keep it running and stick it in a rack, that doesn't make it a TRE. It's still just a computer over which you have complete control, over which other people can't see logs, over which logs may be unclear. So with OpenSAFELY, we wanted to go further. A light touch framework reduces the need for researchers to ever touch the most exclusive raw data, but also allows them to run code against it. Let me show you how it works in practice. So screen sharing doesn't work, and instead I've printed out some nonsense. Hang on a sec. OK, so first up, this is what electronic health records look like. Can you see that? OK, so in very rough terms, it's a series of events, and so there'll be the NHS number, which will resolve to a name. And then there'll be an event code in various different dictionaries, could be SNOMED CT, could be an AMP code, and these relate to a concept like a 2-month prescription of this drug or emergency asthma admission since last appointment. And then there'll be a date and a time, and there'll be a location. So that's the most disclosive raw data. Now, when you want to do research, you want to create a nice 1 row per patient data set, and your 1 row per patient data set will look a bit like this. You'll want a pseudonym instead of the identifier, and you'll have compressed all of these different SNOMED codes for a treatment for asthma, a treatment that is only for asthma, or a diagnostic code for asthma, or a test that relates to a hematological malignancy, or a test that relates to diabetes, or whatever. You want those all to be compressed down to, for example, a binary variable that says, have you got asthma, yes or no? You might have some more complex logic to say, is it mild or severe asthma? And it will all run off essentially searching for event codes within a date range. So when people are working with this kind of data, they work on, give me a sec, they work by building event code lists. So if, give me 1 sec. This is definitely more detail than anybody requires. OK, in the chat, I'm posting content. All right, so that's a list to open code lists. OpenSAFELY code lists. Everybody who builds a code list in OpenSAFELY, they build it in public. The only way that you can execute code lists in OpenSAFELY is via this, by sharing them with the whole community. In the past, people have made code list sharing things, but it's sort of a notice board where you post it ad hoc afterwards, or an appendix, or on request. This is absolutely by default, without question. That's where the code lists go. If you sign up, you can get a login. The code list builder is absolutely beautiful. Lets you play around with parent and child codes in a complex poly hierarchy of different data dictionaries. So if we take, let's say, let's have a look at, hang on, COPD on that page. Give me a moment. Okay, so, oh my God, hurry fast, a little engine. All right, so I'm just posting in the chat a link to the COPD code lists. So if you want to identify whether somebody does or does not have COPD, you'll write some code saying, I want you to tell me if each patient has any, your code list is blocked by your internet blue code. That's hilarious. All right, fine. Here, I'll post some into the chat. We'll see if they come out. Okay, wow. All right, that's good. That's very pleasurable. Oh, look, Teams can cope with a formatted table. What do you know? There you go. All right, so has the person who told me about your internet security policy just been kicked out of the meeting? Oh no, different person. Okay, so that's a bunch of code lists. That's a bunch of codes to identify somebody with COPD. Now, when you run a cohort extractor file in OpenSAFELY, you call those codes. So I've just posted a little code blob, and here you've already done the setup that says, please make me a data set that's 1 row per patient, and it's patients who are live between these dates and so on. Give me a mo, I'm just posting. So here is a Jupyter notebook which you can read through, which gives you the full workflow. And if you're interested, here also is the full documentation on how you drive OpenSAFELY. So going back to that code blob, which I will repost to focus your minds. Rogue backslash, imagine rogue backslash. Okay, so that COPD term, you're saying here, I want you to make me a variable called COPD. It's going to be patients with the following clinical events. And then it says COPD codes. That means it's looking for the COPD codes I posted above. And it's, oh, it's not a complete code blob, sorry. Anyway, and then it says return a binary variable. And then absolutely crucially, it says I'm expecting the incidence of these codes at all in each patient to be 0.05. Now that is really, really important and really special. What you're saying there is I'm expecting 5% of the population to have a 1 for the COPD variable instead of a 0. Now that argument, that cohort extractor code, is used in 2 different ways. It's used first of all to generate a dummy data set, respecting the expectations that you have communicated to the system. And it obviously doesn't work just for binary variables, it works for floating points. So you can say, pull the blood pressure figure, somebody's systolic blood pressure. I want you to take their the average of the last 3 systolic blood pressures. So that will be these SNOMED codes, or these or CCV3 codes, and the associated variable, take the average of the last 3 and then return that in this cell. And you'll also say, I'm expecting the average blood pressure in the population to be systolic of 125 with this standard deviation. The cohort extractor does 2 things. First of all, it generates a dummy data set respecting what you have told it about your expectations. Now that dummy data set is nothing to do with the real data. Synthetic data, I'm delighted and skeptical at the same time. I think the closer it looks to the normal data, the more likely it is to be disclosive. The best way to use dummy data, synthetic data, is to use it to allow you to develop code in the open. And that's exactly what we've done here. So that dummy data, you download the dummy data, it's free for you to use. You yourselves can execute all the code necessary to do all of this yourselves at home. You can download everything to do with OpenSAFELY from github.com/OpenSAFELY. I'm just going to post that in here, although it's pretty obvious from the manuals. So you generate that dummy data, and then locally on your own machine with version control and GitHub and all of the normal delights, you develop your analytic code. Now, when you finished writing your analytic code, OpenSAFELY checks to make sure that it's capable of running to completion. I don't mean people, I mean the machine. And it's checking to make sure it's capable of running to completion. So we're checking that you haven't put a comma in the wrong place, or called a variable that doesn't exist, or called a variable with a capital letter in the wrong place, or any of the other utterly infuriating things that data science entails. And then, finally, when your cohort extractor code is performant, is capable of running to completion, and it's made your dummy data, when your data analysis code, whether it's R, Stata or Python, is capable of running to completion, then and only then does that get wrapped up inside a container using something called Docker, and the cohort extraction code and the data analysis code gets pushed through into the live environment. It executes against the real data, which you never get to see. You never get to download it, you never get to see it. And then out into your outputs folder plops your results tables, your graphs, your logs to understand why your model didn't converge if it's a really fiddly regression. And then that's reviewed, released, and the beneficent cycle continues. Obviously, you can run your code to sanity check your variables to understand whether they're producing what you're expecting, and so on. And that, in outline, is how OpenSAFELY works. That's a very brief description. If we've got